Hello, wonderful audience. Thank you for choosing to spend your time with me. Hello and a warm welcome to our channel. Today, we're delving into John N. Shive. John Northrop Shive, February 22, 1913, June 1, 1984, is an American physicist and inventor. He made notable contributions in electronic engineering and solid-state physics during the early days of transistor development at Bell Laboratories. In particular, he produced experimental evidence that holes could diffuse through bulk germanium, and not just along the surface as previously thought. This paved the way from Bardeen and Brattain's point-contact transistor to Shockley's more robust junction transistor. Shive is best known for inventing the phototransistor in 1948, a device that combines the sensitivity to light of a photodiode and the current gain of a transistor, and for the Shive wave machine in 1959, an educational apparatus used to illustrate wave motion. Now, let's redirect our focus towards early life and education and discover its significance in our narrative. John North Shive was born in Baltimore, Maryland, on February 22, 1913, and grew up in New Jersey. Shive graduated from Rutgers University with a B.S. in physics and chemistry in 1934. He also earned a Ph.D. from Johns Hopkins University, submitting a dissertation Practice and Theory of the Modulation of Geiger Counters in 1939. Shive became a Fellow of the American Physical Society, a member of the American Association for the Advancement of Science, and was a member of the Phi Beta Kappa and Sigma Xi fraternities. In this section, we'll be shedding light on scientific career and its impact on our understanding of the subject. John North Shive joined Bell Telephone Laboratories in 1939. Shive worked initially on physical research and device development, and later on education and training. After retirement from industry, he worked as an adjunct professor of physics at Georgian Court University. The spherical sundial on campus, in front of the bookstore and next to the library, is dedicated to his memory. Let's now enter the realm of transistor development and discover the fascinating stories it has to tell. On January 30, 1948, Shive discovered that gold-plated tungsten point contacts on a p-type layer of germanium grown on an n-type substrate gave a terrific tride effect. On February 13, he also discovered that a transistor consisting of bronze contacts on the surface of an n-type substrate without a p-layer gave gains up to in power. He leveraged this discovery to build a point-contact transistor with bronze contacts on the front and back of thin wedge of germanium, proving that holes could diffuse through bulk germanium and not just along the surface as previously thought. This confirmed William Shockley's idea that it should be possible to build a junction transistor, an idea that hitherto he had kept secret from the rest of the team. Shockley later admitted that the workings of the team were a mixture of cooperation and competition. He also admitted that he kept some of own work secret until his hand was forced by Shive's 1948 advance. Get ready for a thought-provoking discussion as we delve into phototransistor and its impact on our understanding. In 1948, Shive invented the phototransistor that used a beam of light, instead of a wire, as the emitter of a point-contact transistor, generating holes that flow to the collector. Bell Labs announced the invention in 1950. The phototransistor was eventually used in the nationwide direct distance dialing system. In this part of the video, we'll be diving deep into Shive wave machine and unraveling its profound impact. Shive was a gifted lecturer and became Director of Education and Training at Bell Telephone Laboratories. He was responsible for curriculum and administration of educational programs provided to employees of Bell Laboratories. In this new role, he invented the Shive wave machine, also known as the Shive wave generator. The wave generator illustrates wave motion using a series of steel rods joined by a thin torsion wire which transmits energy from one rod to the next. The high moment of inertia of each rod ensures the wave takes several seconds to traverse the entire series of rods, making the dynamics easily visible. The motion is analogous to high-frequency waves that are invisible to the human eye, such as electromagnetic waves on a transmission line. The wave generator could illustrate wave reflection, standing waves, resonance, partial reflection, and impedance matching. Shive made 2 educational films in which he demonstrated the machine, simple waves and similarities in wave behavior, and wrote a book with the same name as the latter. Today, the Exploratorium Exhibit Services manufactures a large-scale version of the machine for use in science museums and schools. As we transition, let's shed light on patents and its relevance to our ongoing exploration. Shive held several patents, including the selenium rectifier and method of making it, directly heated thermocouple, photosystive translating device, selenium rectifier including tellurium and method of making it, apparatus for and method of treating selenium rectifiers, semiconductor photoelectric device, conditioning of semiconductor translators, semiconductor amplifier, and alternating gate current. With the foundation laid, let's embark on a journey into books. Shive authored 3 books during his career, beginning with The Properties, Physics, and Design of Semiconductor Devices 1959, a book about semiconductor devices. This was followed by Similarities of Wave Behavior 1961, a book designed to help college professors teach students about waves using the machine he invented. His last book, Similarities in Physics 1982, was co-authored with Robert L. Weber. He was also one of the editors of Transistor Technology, Volume 1. As we progress, let's zoom in on honors and examine its role in shaping our overall narrative. John North. Shive was a Fellow of the American Physical Society and a senior member of the Institute of Electrical and Electronics Engineers. He was also a chairman of the Advisory Committee on the Pre-College Physics Project of the American Institute of Physics. Without wasting any more time, let's jump into the fascinating world of personal life. Shive was married to Helen Connor, and the 2 were the parents of Peter, Jonathan, and Elaine. From 1974 to 1984, Shive was faculty lecturer in physics at Georgian Court College of Lakewood, New Jersey. He died on 3 June 1984 at the Riverview Medical Center in Red Bank, New Jersey. Get ready to immerse yourself in the world of selected works as we examine its impact and relevance. J. North. Shive, Physical Review, Volume 75, p. 318, 1949. J. North. Shive, Physical Review, Volume 75, p. 689, 1949. J. A. Becker and J. North. Shive, The Transistor and New Semiconductor Amplifier, The Electrical Engineer. Volume 68, Number 3. Ma. 1949. J. North. Shive, The Properties of Germanium Phototransistors, JOSA, Volume 43, Number 4. 1953. John North. Shive and Robert L. Weber, Similarities in Physics. New York, N.Y., Wiley, 1982. If you enjoyed this video, don't forget to give it a thumbs up and subscribe to my channel.